For those of you who just want to get right to it, here you go. This is the circuit I worked up from a few years of tinkering and experimenting. Carefully pry open the base, if you still have your original ballast. Get it out, clean out the old leads. You can assemble all these parts and it will fit inside. We have a CL90 thermistor. We have 4 power resistors, 200 ohms at 5 watts, 18 ohms at 3 watts, 22 ohms at 5 watts, 39 ohms at 7 watts, and 2 1N5408 rectifiers. Again, those are the pins they go to. If you assemble this neatly, put the thermistor at the top so it can radiate heat, it will fit inside this. You can recrimp it, and there you go. Hey guys, welcome to the ultimate guide on replacing the type of ballast used in Motorola 7 and 8-inch electrostatic TVs. That would be the TS-4 and TS-18 chassis. It's a subject near and dear to my heart because I've worked on a lot of these sets. I always need to replace them, and I think it's a really interesting engineering challenge because there are a variety of fundamentally different ways to do it, and I've tinkered with them all over the years. I've also talked about it in a number of videos in the middle of projects, but I've never made a dedicated video really going in depth and covering all the options and why you need them, how they work, and the various ways to replace them with pros and cons, and I'll show you my favorite designs. So what am I talking about? I'm talking about this guy. If you're looking at the back of one of these sets, it's going to be on the right hand side, looking at the back near the AC and antenna inputs. It plugs into an octal socket, but it's actually a perforated metal cylinder, and inside of it are sheets of mica, and they're tightly coiled, I believe it's nichrome wire elements inside, just like a toaster. This gets really hot, which is their downfall. That's why they start corroding. That the heat probably makes the paint degrade. It comes off. They're made out of steel underneath, and they rust. Inside, the contacts corrode, and the wire elements burn open. Virtually every original one I come across is bad, but save them, because depending on what design you go with for the replacement, it's possible with newer components that are smaller, you can fit it inside of this. You can carefully pry this open, take out the guts, and put your new parts inside. And this is one of the nicer original ones I've come across. Originally they would say JFD, Motorola, and then a part number on it. If you are extraordinarily lucky, you may find one that has one of these guys in it. This is an aftermarket amperite replacement. Superior. Talk about why a bit later. Don't ask me for any. I think I have one left. And the only reason I have any at all is I got very, very lucky. Some years ago, somebody came across a stash, a tube vendor, and they were selling them, I think, for 20 bucks a pop or something, and I bought a few. They're glass, but here you can really see the similar setup. It's coiled resistance wire isolated by mica sheets. The later revisions, which the vast majority of sets use, the part number ends with 459. The earlier revision ends with 303. The reason they made 2 different versions is the earliest revisions needed an extra resistive element. The later revisions didn't. For a while they kept using the older style even though that element wasn't connected to anything. Eventually they redesigned this and they used it for all of them going forward. A little crazy, but I got curious about these sets because on the back of all the chassis there's a serial number stamped. And most have a manufactured date. So I started maintaining a spreadsheet, a little database, and a lot of folks over the years have submitted their serial numbers and manufacturer dates to me. So I have a pretty good data set now to know how many they made of each chassis revision and how many of these they made in total. I can tell you, they made about 100,000 TS4 chassis and 100,000 TS18 chassis. I see people make comments, oh, they made millions of these, it's the most common early TV. It is a very common early TV, but across all the models, 7, 8-inch, everything, they made about 200,000 total production run. So I think there's a lot of them around because they're small, you can just throw them in a closet, whereas the consoles would get scrapped out. But the early ones, the A, the B, the C, the D, the E, the H revisions, F, there aren't that many. Some revisions they maybe made a few thousand of, and that's it. So there are some I've never seen. I've never seen an F. I don't think I've ever seen an E. But at any rate, this is a J. That's what you're most likely going to find. That's what we're going to talk about for the most part in this video, is how to make one of these that will work in the TS-4J and TS-18 and TS-18A. If you are a fan of these sets, as I am, I suggest you try to get yourself an original service manual. They're out there, originally sold for $1. This is for the earlier 7-inch sets. There's also one for the later 18-inch sets. Very thorough, comprehensive service manual. And back, they have this neat fold-out section with schematics for all the chassis variations. So this is what we're going to be talking about in the majority. The TS-4J late. Nice big form factor, so rather than messing around with a Sam's Photo Fact and whatnot. Isn't that nice? And this is the ballast. This appears to be the best breakdown of how the power supply works that they have in the service manual. So we have our AC line coming in. One side goes via a switch right to B-. It's a floating chassis, it's not a hot chassis. The other side goes into the ballast tube. And it branches out through 3 of those resistive elements. One goes down here, one goes down here, one goes off to the right. So inside this little diagram, that's that pin that has 3 resistors coming off of it. And then there's one resistive element floating by itself. That is this guy. Okay, well, we're replacing 4 resistors. They give the value right here. What's the big deal? Grab some power resistors, throw them in there, and we're done. Yes, yes, you can. And many restorers have. And it will work. But some things to consider. One, it will get just as hot as the original did. So you're going to have mounting considerations. You may want to mount them to the chassis with some thermal paste, which means you're going to have to find a spot to mount them, drill holes, reroute wires. That's not much fun. You will have a tough time cramming them inside of the original housing if you want to reuse it. If you do, it's going to get really toasty in here so much so you may want to crimp your joints rather than soldering them, because the solder might start to fail. You're going to need to use that heat shielding above it. All that aside, you're going to lose something very important, which is Inrush current limiting. Notice these don't say ballast, they say automatic regulator. Yeah, the material these are made out of is carefully selected such that it tries to maintain a constant current flow through the circuit. These guys are essentially temperature independent, meaning the resistance does not change over a wide temperature range. These are very much temperature dependent. The hotter they get, the more resistance they have. That's what we would call these days a thermistor. That's a really nice property to have, the way these are used in the set. If you watch one of these in operation when the set is cold, as soon as you turn the set on, these will flare up bright red orange, and then they cool down to be barely visible. That is the effect of when you turn the set on, there's a big rush of current into all the circuits, these resist that by flaring up and taking the brunt of it by generating a lot of heat, which means the rest of the components in the set don't get that punch in the face, so to speak, when you turn the set on, which could potentially shorten the life of a rectifier or a capacitor or a tube filament. It's nice to have Inrush current limiting. So that's where the engineering fun comes in. There are a number of ways to simulate the effect of this current limiting while also reducing the amount of heat produced. And that's what you see in here. These are some experimental designs and parts I've monkeyed with over the years. You may be very familiar with this from working on radios, which also, the lower end models of the transformer-less sets often have some type of ballast or current limiting device. And over the years, experimenters have realized that there's some other ways to do it besides just a thermistor or a resistor. You can do it with a capacitor or a diode, depending on the exact parameters of the circuit. So, this is an example of using some capacitors in place of resistors. You can also do it with diodes. You see in here, there's a couple of tiny diodes and a thermistor. So we are going to go over several distinct ways to do this. One, pure resistors, one using capacitive reactants, and one using diodes. Let's take a little excursion into talking about what the two main elements of this ballast are used for. And that is the tube filaments. There are two fundamental ways we can power the filament. One is if we have a power transformer with our primary going to the line voltage, and say we have a 6.3 volt secondary, we can just connect all of our tube filaments up to that and put them all in parallel. Fine and dandy, assuming all your tubes actually run on 6.3 volts. Now, there's something else to think about. There's two ways you can think about how the tube filament works. One, we could say a tube like a 6AU6 needs 6.3 volts across the filament. Or we can think about it in terms of the current, and we can say a 6AU6 filament should have 150 milliamps going through it, regardless of what the voltage is. And that's what we're doing in the case of the Motorola. We don't have a power transformer. We can't hook up the tube filaments in parallel because all we have to work with is 117 volts coming into the set. Now, in the case of radios, like an All-American 5, we can string, classically, 5 tubes in series. 35W4, 12 AV6, and so on, such that they add up to about 117 volts, give or take. Sometimes it's a little less, and you may notice on your AA5, there's a little resistor thrown in before you get to all your tube filaments, which then just wrap around, and we have a power switch down in here. That does a few things. One, if these don't add up, so think about, say each tube has, maybe we have 35 volts, 12 volts, 12 volts. They should all add up to 117. Typically they don't, so you'd add a resistor in there to drop a few volts across it. But it also limits that surge current when you turn it on. And sometimes you'll see people suggest adding a CL90 in here. The thermistor symbol would be something like that, which means the resistance can vary depending on its temperature or the current going through it. So as I said, another way to think about this is forget about the 35 and the 12 and the 12 and the 50 and so on, and just say, hey, our goal is to have 150 milliamps going through these tubes. Now let's flip over to the Motorola TV. TVs have more tubes in them. So, unfortunately, Motorola engineers, clever as they were, and this is a very clever design, they just couldn't make it work. They couldn't take, even if they used all 6-volt tubes, it just, the math doesn't work out. Especially because there is one tube that sticks out like a sore thumb, and that is the 7JP4. The picture tube. It needs 600 milliamps, which is standard for picture tubes. All the other tubes, your 6AU6s, 6AL5s, have 150 milliamps going through, sorry, 300 milliamps going through them. So if we were to say, great, well, we'll just string a whole bunch in series and connect them around and we're done. Or if we need to add a little resistor, fine, we're done. Except this does use 6AU6s and 6AL5s, and they need 300 milliamps. That's a problem. Fundamental law of electronics is you have a wire, you can only have one current going through it. The current through every single thing in this circuit has to be exactly the same. We can only have 300 milliamps going through this, or 600 or 450, whatever it is, every tube is going to have the same amount of current going through it. So what did they do? I said, okay, we're going to be clever and we're going to have two 300 milliamp strings. So they tapped in here, and fine, we'll have some more tubes going up here. And then we're going to join them together, and we're going to take the sum of that and go down here. So we have 6AU6s, 12AT7, 6AL5, 12SN7s, all with 300 milliamps going through them in two separate strings that join up at the end, and the last guy in line is a 7JP4. So 300 milliamps, 300 milliamps, 600 milliamps. Awesome, except for one thing. Now we don't have enough tubes, and if we add these all up, we're far shy of hitting that 117. If you add up all your 6AU6s and 12SN7s in each of these strings, and don't forget to add this guy, we are around more like 85 volts on each section here. So we need a combination of about 85 volts from here to here, which will result in about 300 milliamps through here and 600 through here. Okay, we need something to fill the void. That's where the ballast comes into play. I suppose if you wanted to, you could just add a couple more tubes in here that did nothing, except burn off energy, which is what the ballast is doing. It's substituting for some more tube filaments to make this add up to 117 when you do all the sums of all the drops across all the tubes. So what they did is they throw that ballast in. Now, one immediate thought is, well, hey, we have two of these, right? And they both get really hot. Couldn't we connect this up, and say, just put one down here? And then we just cut our problem in half. Instead of 105 ohm resistors, resistive elements, why don't we put a single in? I suppose you could, except it's going to get twice as hot. And they already individually get really hot. So they chose to go with two separate resistive elements. Alright, so that is the reason why two of the resistive elements exist. They are simply there to make up the difference because all of our tubes and our two strings don't add up to the full line voltage. You got to put something in there to make up the difference. Okay, what about the other two resistors? Well, let's go back to our mains 117 volts coming in from our wall outlet. We got the tube filaments covered now, but we need a plate supply. We need some high voltage to make all the circuits work. We don't have a power transformer. Well, one simple thing you could do is just take a half-wave rectifier, just a single diode, throw a filter cap in here, and call that our B+. The problem is if you do that, this is only going to be around 130 volts or so. That's not enough. So somebody came up with a clever circuit called a voltage doubler, where we can essentially double that voltage and get 260 out of it or so. This uses selenium rectifiers, which do have a lot of losses associated with them, so you do lose a bit. So, voltage doubler. This may seem crazy, but right off the AC line, you put an electrolytic capacitor. Normally, if you put AC line right across a capacitor, it's going to explode when you get reverse bias or rupture. But this has diodes right after it, and that's what makes the magic happen. So right after this, we have one, which also seems kind of crazy at first, going to ground, and another one going off this way in the positive direction. And then here we have finally our other capacitor, which does the main filtering job there, and then this we can call our B+, and this will be 200 and change. Okay, so where do those two other resistors come into play? Well, just like with the surge on the tube filaments, there'd also be a surge in this circuit when you turn it on, because these capacitors will be discharged. They'll look like a dead short. They used selenium rectifiers when they made this back in 1948 or so. They cannot handle high surge currents. Not so nice on the early electrolytic caps either. So, one resistor they threw in here. Inrush current limiter. That's all it's doing. And that's the 37 ohm guy. That value is not at all critical. By that I mean you could use 22, 27, 33, 39. It really wouldn't make any difference. But here's the other thing. I recommend you replace the original seleniums. They don't age well. They tend to get lossier and lossier, which means they run hotter and hotter, and your B+ it droops and droops. Eventually they can fail, and when they do, they release some very nasty selenium gas. Okay, great. So we replace them with modern silicon power diodes. They are far more efficient, which means your B+ will be even higher, but also they can withstand considerably more surge current. Enough that the ESR in this cap will probably be enough to protect them, and you could just eliminate that entirely. However, if you do that, because these are more efficient, your B+ is going to go up even more. So I suggest you do leave this in, perhaps even increase it a little bit. Not so much to protect your modern new parts, but to keep B+ about where it was originally. So you're going to basically burn off some power here to compensate for these being more efficient. Now, that takes care of three of them. What is the last one used for? Well, these do a pretty good job of filtering the ripple out of the B+, but you know, there's an even better way to do it, which is to add yet another cap and put a resistor between them. Call that a pi filter. So it kind of looks like the pi symbol. That's an RC low-pass filter. That's where the third resistor comes into play, and they use a much larger value there of 200 ohms. Again, not critical. You could use 180, 200, 220. Wouldn't make a whole heck of a lot of difference. But the end result being that the B+ here has even less ripple than at this point. If you put a bigger cap here with low ESR and you put beefier diodes in here and they're more efficient, it's probably not as necessary, but it also drops some voltage. So if you eliminated this, hoping to eliminate one of those ballast resistors, your B plus is going to go up, which may potentially cause a problem, like stressing out some other components or causing the scan to be too large and go off the side of the screen, that kind of thing. Now keep in mind, these early sets had no voltage regulation. This voltage could be ranging from, say, 110 to 130. The sets would work. That's why they have controls like size, like width and height, and that is to adjust it for your varying input voltage. And as these components age and there's tolerances and all that, your B plus, figure whatever they say in a schematic, plus minus 20%, you're fine. But anyway, so these are the other two we want to replace, the 37 and the 200. Let's talk about the filament droppers in more detail. Those are the two elements inside that ballast that dissipate the most power. Power is current squared times resistance. We have two filament strings, each is 300 milliamps or 0.3 amps. So if we do 0.3 times 0.3 times, they show 105 ohms on the schematic, that's 10 watts. We have two of them in there, so that's 20 watts. Might not seem like a whole lot, but in a small form factor inside of a small box, it gets pretty darn toasty. And there are two other resistor elements in there as well. And the four together, it's probably in the neighborhood of 35 watts. That, and again, in a small package, is pretty significant. That's our challenge, if we choose to accept it, is to reduce that power consumption and still have a soft start on power up. Again, you don't have to. You can put some big old power resistors in there and just let that area of the chassis get hot. That's fine. That will work. So let's just show that version of it. That's the simplest version. So we have our AC coming in. We have the one side going to return. We have our two filament strings. So we could simply, just get a couple old. Now, for safety margins, it's a good idea to double the wattage, so the calculations come to 10 watts. Let's go with 20 or 25 watt resistors. And they show 105. You can't really get those. The AC line today is probably more like 125. So if you're going to go with this, I would go with the 120s, which are pretty readily available. And I would get at least 20 watts or better. Yes, they are larger, but in that confined space, they're going to struggle to radiate the heat, which means they get derated. When a resistor says it's good for 10 watts, that's 10 watts with a good heat sink or ventilation. When you start confining it more, the power rating goes down. So I'll go with at least 20 watts, unless you're going to chassis mount it, in which case you can maybe get by with a little lower. But it's a really good rule of thumb is to do it at least twice the calculated wattage. And then these go to our tube filaments, and everybody's happy. But there are two other ways we can do this. Now let's talk about doing it with capacitors. May sound crazy, but yeah, we can do it with capacitors. So we have our same AC coming in, one side going to the return. The other, we have our two branches going to our filament strings. Instead of resistors, we put capacitors in, and then we have our tube filaments, and they join up, and they go around, and they go to our CRT filament and back to the return. Well, what the heck? These are fundamental things. We have a resistor, we have a capacitor, we have an inductor. Those are the three fundamental components, right? How can this act as a resistor? There's a void there. No power can get through. Actually, it can, because this is AC. We have a sine wave here that can get through. Capacitors do an interesting thing, as do inductors. They can introduce a phase delay. So let me draw this a little bit neater here. And let's say put this on a scope and we're measuring voltage, and we have time and we have voltage, and we're going to have a nice sine wave. For voltage, but there's also current. I'll use a different color for that. And on the input side, let's say they're in phase. Power is voltage times current. Well, it hits that capacitor, which has a load on the other side, and that will introduce a phase shift. And the phase shift depends on the value of the capacitor, the frequency, and the load. So on the other side, what's actually getting to the tube filaments is not going to be this. Again, I'll do, say, voltage with black. But on the other side, the current will have a phase delay. So at any point when we do our V times I to get the effective power, it's going to be less because they're out of sync, which means less effective power gets to the tubes, and this limits the power getting to them. The calculation to figure these out is a little complicated. However, other smart folks have already figured this out. I'll give you a link to a spreadsheet where you plug in your frequency, your input line voltage, the amount you want to drop, and it'll figure out the value of this capacitor. The neat thing about this too is that when the set's cold, the tube filaments are cold, they have a lower resistance, so you have an inrush of current. The phase shift on this will be more. It'll act as an inrush current limiter, so it'll act like one of these guys, and you don't need to add a CL90 to it. So you might think, hey, that is the perfect solution. I'm going to use that for everything. There are downsides. There are trade-offs to all of these designs. AC-rated caps are big, and they're expensive, and they're hard to find. They only come in limited values. I cheated a little bit on my prototype here. These are 250-volt DC capacitors. A lot of these film caps, polypropylene, polyester film, they don't even list the AC rating, or if they do, it's going to be significantly less. So these are 250 volts DC. They might be good for 80 volts AC. These are rated for 250 volts AC. I got lucky and I hunted around. I think they use these in ceiling fans. But look how big it is. If I tried really hard, maybe I could fit a couple of these inside that original housing, but that's not going to be too easy to do. And these are upwards of $10 a pop. So that's the problem. Another problem is, if I do the math, maybe the ideal value for this is 11 microfarad or 14 microfarad. Those aren't standard values. You can get 8, you can get 10, maybe 12. The good thing, though, is you can fudge this a little bit. All these components have a certain tolerance, plus minus 20%. Tube filaments are good for plus minus 10% from their ideal current rating. And it's somewhat self-adjusting because of the reactance varies with the load and whatnot. I can already tell you the values. If you use something between 8 and 10, you'll be fine. But those are the downsides, is the physical size, the cost, and the availability of the components. Alright, there is one more way we can do this, and that's with diodes. I'm going to switch colors here just to break up the monotony a little. So, here's our two branches. Instead of resistors, instead of capacitors, we put diodes in here. And then we have our tube filaments. And there we go. Now, the way these work is, let's put up our little sine wave here again. So we have sine wave coming in right off the power line. but it's a half-wave rectifier. So what do? They rectify the AC and DC, and they do that in half-wave configuration by just we lose half of it. You might think, oh, it's going to cut the power in half. No, it's more complicated than that. Again, luckily somebody else has figured out the math. It knocks something like 20–25% off. And there's nothing you can adjust. Capacitors, resistors, you can use different values of the components. A diode is a diode. So what you very often need to do is add some additional resistance here. So you still very likely need some power resistors. But diodes are extremely small. You can see this little prototype I was working on here where I added some series resistors. So the resistors are large, but the diodes are tiny and they cost virtually nothing. That's why I like this design. It's extremely compact, very cost effective, and it gets the job done. However, this, like doing the pure resistance, offers no inrush current limiting. So I typically add a thermistor to it. So you end up with a thermistor and 2 power resistors and 2 diodes. So the component count is a little higher, but it still cuts the power consumption down considerably. These power resistors are pretty small. They don't dissipate a whole lot of power. 3 watts, 4 watts, something like that. So we still have significant savings, and it's small and it easily fits inside of the original housing. So this is what I'm going to go with and primarily talk about in this video. One other downside to this, though, is it's really hard to measure what is actually going on. With pure resistive, you can put an ammeter in the circuit, or you can check the voltage drop across each tube filament. Likewise, with the capacitors, you can measure the AC voltage drop across each tube filament. And this you can't, because you have a complex waveform. And if you're thinking, oh, well, I have a true RMS voltmeter, great, it won't work. Because the output on this is actually a combination of DC plus a complex AC waveform. Very few meters can handle that properly. You're thinking, oh, well, I'll measure it in DC mode and then AC mode and add them together. That doesn't work either. There are a few meters that can do it properly. I believe the Dave of the EEV blog designed his own multimeter. I think his can, where it has the proper circuitry to handle a complex AC plus DC waveform in one shot and give you the correct value. So how do you know it's working properly? 1, trust the math. 2, if you are familiar with working with tubes, you know how brightly the filament normally burns, and you can just eyeball it. If the tube is getting too much current, the filament's going to glow really bright and eventually burn out. If it's super dim or dark, it's not getting enough power. If it looks a normal orange color, you're probably doing okay. So when we do this, I can compare it to, I'm lucky I have some real ballasts, and we can observe how the tubes look with the real deal, and then we can put in our prototype and we can observe how it looks, and of course how the set operates. Let's see if we can get this open. The base is identical to a octal tube. It's bakelite and then painted steel. It's crimped at 4 points. It's tempting to just stick a flat-plated screwdriver in here and bend up, which you can do, but be really careful because you're very likely to blow out some of this bakelite. Or you could take some needle nose pliers and get in there and try to flatten this out. It's tough to do, and you might also chip this and mess up the metal. I don't have an answer for you. These are just the things I've done in the past, and we'll do the best we can. This is pretty pretty thick metal. Yeah, I'm gonna go with the needle nose plier approach. Been a while since I've done one of these. The reason it's so difficult is they crimp the metal down so much. It's just about flush with Bakelite, so it's hard to get anything in there, and you have a very hard surface against a very fragile surface, or very strong surface, I should say. So you do the best you can. Alternately, get yourself some blank Bakelite bases. Some vendors sell them here and there, or take a burned out octal tube, bust up the glass, rip out all the insides just to get the base and the pins. You can heat these up, pull the leads out, and reuse one of these. Just make sure it has an actual pin at all the positions where you're going to need it. Well, we'll see what we can do. Just realized when I pushed this down, the whole thing shifted over a little bit. So there's a little bit of leeway. And go back to trying a screwdriver. Once you get it started, it starts to get a little bit easier because you get a little. There we go. Okay, so I got that one. So once you get it started, it loosens up and you get a little more room to. Actually, it's going easier than I remember. I'm not really leveraging up, I'm just pushing in. Just be careful not to slip and jab this into your hand. This reminds me of uncrimping electrolytic caps. I have some battle scars from doing that. Hey, that actually, alright, so there you go. There's my tips for doing this. Get yourself a small flat blade jeweler screwdriver. And instead of doing the obvious thing, which is to go down and bend up, and that's when you blow this out, just push straight down. And the wedge action of this blade will pop that metal out. Not quite. It's still hung up a little bit. Not sure where. Maybe on this one that looked to be pretty well bent out. That feels like something's hung up inside. There we go. Ooh. Now you get to see what's inside one of these. A very crusty, all original one. And that, my friends, is why they go bad. How nasty that is. So we have green corrosion all over the place. These dabs are some type of refractory cement that's supposed to hold these coils of wire firmly against the mica. They routinely fail, and then the wires go flopping around. They can short into each other. They break loose. They go open, and there's a glob at the top with another piece of mica. Basically, this whole thing is just disintegrating. So we are going to get it out of there. I'm going to start out by clipping the leads. There we go. We can dispose of that. Nothing toxic. There's no asbestos in there. It's just mostly mica and some wire. Now we have all these stubs of wire. These pins are hollow. We heat them up from the backside, and we can, with a soldering iron, we can pull these leads out one by one. Because this is perforated metal, of course, all sorts of dust and dirt has gotten into this over the years. We'll use a little toothbrush or something to clean that out, get this all nice and pretty. Then we'll have a base to work on. This, I think I have some black spray paint that's rated for engine use. In other words, high temp enamel. I can hit it up with that. My downside is I'll lose what remaining traces are of that Motorola logo. I really don't think the owner cares. He just wants a working set back. Now back to the schematic I showed at the start. I want to walk you through it a little bit and explain why I chose these parts. This is our AC line voltage coming in. I assumed 125 volts for my calculations. To get the Inrush current limiting effect, I added a CL90 thermistor, which will go to all three branches. The outer two branches go to the filament strings, the inner branch goes to the B+ voltage doubler. Originally this was 37 ohms, I dropped it to 22, partly because I'm getting some resistance here, which is about 5 ohms or so. But also, the higher the resistance I put here, the higher the wattage I'm going to need, the hotter it's going to get. I wanted to get a reasonable compromise. I wanted something that was small so I could fit it inside that housing. Plus, I'm replacing the seleniums with pretty rugged power silicon diodes, so they can handle a pretty good surge current. But I did want to drop some voltage here, so I compromised at 22 ohms and 5 watts. Now the outer two, I mentioned earlier, if you go through and you very carefully calculate all those tube voltages, your 6.3s and 12.6s and 25s, you will find out that one string is 81.7 volts across all the tubes on that string, and the other is 75.4 across all the tube filaments on that string. They're not equal. Well, if you plug those values into the diode dropper calculation and figure 125 coming in, you get about 18 ohms of additional resistance you need to add to one of them and 39 on the other. And with the wattage, adding a safety margin, 3 watts on this guy and 7 on that guy. That's the biggie. That's the one that gets the hottest. Finally, the one that's as part of that pi filter, I just left the value the same, 200 ohms, and it turns out 5 watts is plenty. Here is what the components look like. The biggest one being the 39 at 7 watts, and this is the 22 ohm 5 watts, and 200 ohm 5 watts, 18 ohm 3 watts, our two 1N5408s, which are definitely overkill, but they cost pennies, so why not? They're very rugged. And finally, I use the small version of the CL90. You can get these in different disc diameters. I went with the small one basically so it would fit in the housing. When you construct this, put the thermistor at the top so the heat radiates out the top, and you want this to cool off quickly when you turn the set off. So if you turn it back on soon, it needs to cool down to do, and then heat back up to do its thing. But I also wanted to keep it away from the diodes, so the diodes are going to be mounted down near the bottom and the thermistor will be at the top. Silicon doesn't like heat, so we want to keep the heat away from it as much as possible. So you can see this isn't much space-wise. It easily fit inside here. So that is our next challenge, is to take our cleaned off base, cleaned out the pins, and start putting it together. The diodes are the easy ones because we can simply just stick them right down in the holes. And then we can attach other components to them, and we're kind of going to just build everything up 3D, stick parts where we can into the holes, and attach other parts to them, and just twist the leads and do J-hooks and solder everything together. It's pretty easy to do. And while you're doing it, just occasionally slide this over, make sure that everything is fitting inside there. Alright, let's get to it. I started out with the diodes because those are the easiest thing to do. I cut the leads such that they just stick out a little bit from the base, fed them down into the hollowed out pins, and put a little solder into the ends. Alright, so it's on 2 and 7. Now let's do the 22 ohm 5 watter that goes to pin 1. Remember, you're clockwise when you look at the bottom, starting with the key. So this is pin 1. So we want to put this in here. I want to go all the way down because I wanted to keep the heat away from these. Plus, we have quite a bit of vertical space, so I want it situated so it's about here. So I'm going to trim it off, but this yay much, and put it down in there. Oh, it's going to be nice to have 3 hands when doing this, but here, let me get this propped up, and I'll do this, and we'll do this, and heat the side of the pin. And feed. Woo! So that's what I was trying to avoid. Some of these leads are small enough that they will just slide right through the center. That's alright. Tell you what, we're just going to dab a little on the end so it holds it in place. And we'll come back and we'll re-tin up all those once we get it assembled. Because once I get the other end attached to something, it'll be more secure. Alright, now let's do what goes to the ends of the other 2 diodes. Let's also give some thought to where the 200 ohmers got to go. So 200 goes between pins 3 and 4. 1, 2. So between these 2 pins. So I could do that, but then it'd be close to that. So I would suggest to go over here, and then I'll bend this lead around, and I'll have to add a little extension wire on there so I can feed it down. Neater job on that. Something like that. And that's 1, 2, 3, 4. So it's going to go in like so. Let's tack that in place. So that takes care of, I think, all the pin. Oh no, we still have a 22 5 watts. Oh no, sorry, we took care of that. Yeah, that takes care of all the parts that need to go right into pins. The only pin left is pin 6, and that will just be a wire that goes to a bunch of stuff. So next up, let's do the big guy. That would be the one that goes to pin 2, so 1, 2, this guy. We need to add this resistor to this diode, and we need to make sure it's still going to fit within this. So if we do it around about there, down a little bit, join them up kind of around there. I'm just bending both leads over, making J hooks on them. I'll squeeze them together and then I'll solder them together. These diodes have pretty beefy leads on them. That's why I don't need to add any structural support. These leads are so fat that they can support. They offer enough support, I should say. It's easier to work when you don't have a camera kind of in your way, and you're not concerned about keeping things in frame. Alright, get this guy out of the way. That'll do. I'm not bothering with heat shrink tubing or anything like that. For one, this gets pretty warm, and I think the heat shrink tubing might not be too happy with all that heat over extended periods. And as long as you're neat and keep things away from each other, nothing should ever be shorting in. I said these leads are so beefy that these parts aren't going to move. Alright, now let's do this guy. Let's go on to this. So, similar deal. Cut some excess off. Make J-hook. Do the same on the other end of this. Trim a little off. Make a hook. Hook them together. Squeeze. And solder. Okay. So these three ends all connect together. That makes that part kind of easy. And if you did your lead lengths right, you don't have to add anything else. They'll be long enough that they can all connect together. Just want to space things apart a bit. So get this coming in from the side a little. Let's check. Get close to the top, but we still have room. Cut that off. And let's tack those three together. Alright, almost done. What's left is this guy and this guy. Or sorry, no, we don't need that guy. We already got our 4 resistors in there. We need to add this. So this will go between pin 6. Which is 1, 2, 3, 4, 5, 6. Down here and this. So I'm going to mount one end to this up here, and then I will run an extension wire down to pin 6, and then I need an extension wire on that guy, and we're done. Here is the assembled unit. I did end up putting some tubing over the lead up to the thermistor on the top. I think it'll be alright. My concern was that if it's right next to something that gets hot, over time it might start deteriorating, but I think it's best to put something over it. So that is the main AC line coming in, up to the thermistor, branches out to 3 resistors. These 2 outside ones go down to the diodes, so that goes to our filament string. The center one goes to the voltage doubler, and there is our 200 ohm resistor for the pipe filter. That's it. Just eyeball it to make sure everything's pretty well centered, and there she goes. And we just need to line up the marks and then recrimp it. I suggest you put it in the circuit and try it before you recrimp it, and that's what we're going to do next. Let's start out by using a glass amperite ballast. I'm going to power this up. We may see a brief glow in this. What I really want to see is the filaments and the tubes. They should be dim at first and gradually light up, rather than having a bright flash right away. This should limit that surge current. I'm going to turn off all the lights to really increase our chances of seeing this. And here we go. Yeah, there was a brief orange flare up, and now the other tubes are starting to light up. I'll put a bit of lighting on so you get a better idea what's going on here. Alright, so we have that typical nice orange tube glow, and I'm using a green phosphor CRT while testing, because the big goal here is to not damage an irreplaceable 7JP4. Alright, so of course the commercial ballast works. Now let's see if our substitute works. These do get really hot, so be very careful when removing them. They get a lot hotter than a regular tube. Make sure you have the set unplugged when you do this. You don't want to get shocked. Depending on how you have this plugged in, you could have live AC on one of the pins. Alright, so that's that. Plugged in, and we are going to turn it on now. Good, perfect. Took a long time for the tubes to light up. Actually, took even longer for the tubes to start lighting up with this than with the amperite ballast. That's because of that CL90. And here is our CRT coming to life. I would say we were successful. And here it is with no lights. And I can smell the heat coming off of that CL90. Don't worry, they're supposed to run hot. It's rated for 2 amps continuous operation. We have less than an amp going, well, about an amp going through it, I'd say. All the power for the TV, in fact, is going through that thermistor because we have it on both filament strings and the B+. Alrighty, so all that's left to do is to optionally repaint the perforated metal tube, crimp it back on. Of course, leave this out running a while to make sure everything is correct. I'm going to leave you off with, I will draw up the other 2 variations, which the fixed resistors and with capacitor droppers. Alright, here is the purely resistive version, and notice how big these are. These are the ones adjusted for 125 volts coming in with the proper filament voltage calculation. Yeah, these are larger than the 105 on the schematic. As I've said, they modified the design over time. 105 is not enough if you want 300 milliamps through each of these 2 strings, especially with higher line voltage. And I had the thermistor as with the diodes for the Inrush current limiting. So 150 ohms at 25 watts, 130 ohms at 20 watts. Here's a design using capacitors. Same 200 ohm 5 watt, 22 ohm 5 watt, 2 resistors, 18 ohm 3 watt, and an 8.2 microfarad non-polarized AC rated cap, and a 10 microfarad AC rated non-polarized cap. These resistors I show across them are bleeders. I recommend you add them, say 220K 1 watt. If you don't, when you turn the set off, depending on where you are in the power cycle, the AC line coming in, there could very well be a charge across these. I have gotten zapped. After the set was off for quite some time, I went in and pulled one out that I was working on that didn't have the external metal shield around it yet, and yeah, I got zapped. Those plastic film caps will hold the charge a long time. So I highly recommend you add some tiny bleeder resistors across there to bleed off that charge. Now, I say it's a design. You could also use 8.2 for both and increase the value of this resistor. That'll generate more heat. That is exactly what you are seeing here realized. Let's pop this in and I'll show you how this looks when you power it up. Notice no thermistor. Yeah, we're not getting a thermistor on B+, but this will limit the surge current, and then the caps inherently will limit the surge to the tube filaments. Alrighty, same as before. Let's dim the lighting and get everything in frame nicely. And here we go. its own. This has the longest startup of any of these. And here we start to go. Tubes are lighting up. I think this is the most elegant solution, the coolest solution, literally and figuratively. If it just wasn't for the availability and the cost of those darn AC film caps and the physical size of them, I would use this all the time. But the diode version works fine too. The difference is, man, there's nothing. There's just bare, I can't feel it. If I turn it off and touch the resistors, I'm sure they're a little bit warm, but that just runs really, really cool. So there you have it. I'll leave it up to you. Resistors, diodes, capacitors. Hope you enjoyed this in-depth look at replacing the ballast found in every electrostatic Motorola TV. And I hope you are successful with replacing yours.